In this lesson, we're going to look at segments, and we're going to start with chord segments. And remember, the chords are the line segment that start and end on the circle itself. So here I have intersecting chords, and each segment I'm labeling A and B and C and D. So this is pretty wordy. It's kind of hard to explain it all in words, but here we go. If two chords intersect within a circle, the products of the measures of the segments of one chord equals the product of the segments of the other chord. So the product of these two values are going to be equal to the product of these two values. So let me write that out. If I'm given those four segments, A and B and C and D, that means A times B is going to be equal to C times D. And there is a way to prove that. We might do that in class, but for now we're going to focus on numerical examples. Alright, so here's an example. Let's say AE is equal to 8 and EB is 4 and DE is 12. Okay, we want to find EC. So that's the other segment that we don't have yet. So let's look. We have AE is 8 and EB is 4 and DE is 12. We want to find that segment right there. Well, according to the theorem, 8 times 11 is equal to 12 times x. Or not 11, 4. It looks like 11. 8 times 4 is equal to 12 times x. That's what I get for not being able to read my whole handwriting. So let's look at this. 8 in symbols, it's AE times EB is going to be equal to DE times EC. So 8 times 4 is equal to 12 times EC, which is what we want to find. 8 times 4 is 32. 32 is equal to 12x. So x is going to be about 2.6 repeating. And that's how you do it. It's pretty basic, really. Now that's when the chords are, when you have two intersecting chords. The next thing we're going to look at are two secants, which you can see in the diagram here. Okay, so once again it's pretty wordy to explain, and even then I cut some corners, but it's the product of the measures of the whole sequent, this whole secant, times the external segment, and that's going to be equal to the other side, the whole secant times the external segment. So we don't deal with the inside chord at all. It's whole times external is equal to whole times external. So that's how you think. Whole times external is equal to whole times external. Whole times external is equal to whole times external. In letters from this guy, if you look, it would be AB times its external, which is DB, and that's equal to the whole on the other side, CB, times the external, which is EB. So we don't use AD or CE. Alright, so let's work a numerical example for this. We have given AB is 8, and BD is 3, and BE is x. So we're going to label AB as 8. This entire thing is 8. BD is 3. And BE is x. And then we need EC. So this is a little bit different. EC is going to be x minus 2. We want to find the value of x, and then we'll find BC, that whole side. Well, if EC is x minus 2, we have to be careful. We don't use EC in our formula here. We have to use the whole thing. So whole times external is equal to whole times external. Well, on the one hand side, it's going to be 8. 8 times 3, and that's equal to the whole side is going to be x plus x minus 2. So that whole side is going to be 2x minus 2, and then the external is another x. So when we look at this, we end up with a second degree equation. If I divide through by, we'll put it in standard form first. 0 is equal to 2x squared minus 2x minus 24. I can factor a 2 out of each one of these things and divide it away. So if I divide everything by 2, I get x squared minus x minus 12. That's a little bit easier. Factors of 12 that have a difference of 1, that's going to be x minus 4 and x plus 3 because the center is minus. Make your t, and you say x minus 4 is equal to 0, x plus 3 is equal to 0, so x either has to be 4 or negative 3. Well, we know it can't be that because that's a length, so we have to use x is equal to 4. I'm running out of room here, so I'm going to have to go over here. And that means that, so x is 4, BE is 4, and then we want to find BC. BC is 4 plus 4 minus 2, so BC is going to be 6, and there's your two answers. So sometimes you're going to have a second degree equation, but you should know how to solve a second degree equation, especially if it's factorable. That's pretty easy. Now we can also do this with a tangent and a secant. So here we have the tangent and we have a secant. For the tangent we don't have any internal, so the whole and the external are the same. And that's why it's the square of the measure of the tangent, and that's equal to the whole times the external on the other side. So this one is tangent times tangent. So tangent, tangent, which is really whole and external because they're the same, and that's equal to whole times external. So we will work one more example like that and finish this in class. Alright, here we go. We're given that AB is 4, so there's my tangent. AD is x, and CD is 3x. So this is similar to the last one we did, so we have to be careful. In this case I have a tangent and a secant, so it's going to be 4 times 4 is equal to the whole length times the external. So 4 times 4, we got 4 squared, that's the tangent side, is equal to, now the whole side is an x plus a 3x. So that's going to be 4x. 4x times the external, which is the other x. So here we have 16 is equal to 4x squared. This is an incomplete quadratic, so I can divide the 4 away, and I have 4 is equal to x squared. Taking the square root, I know that x is going to be positive or negative 2, but since this is a length, we're not going to deal with the negative 2. So we just have x is equal to 2. So coming back and answering the question, we want to find AD. AD is 2, or we want to find x, which is AD. And then AC is 4 times 2. AC is going to be 8. So we'll work a lot more of these examples in class. All you have to remember is whole times external is equal to whole times external.